All right, so we're going to get started tonight, and with me is Rodney Chai, one of our meteorologists, and of course, I'm Joe Deli Carpini. Tori was going to be with us. He's at the office tonight. He's a little busy helping out, so he will not be with us tonight, but you can see his smiling face anyway. He did help us with the presentation, so you'll have Rodney and I to take you through this event tonight. So, Rodney, I'm going to let you start it off talking about the flash flooding, and then I'll come back to talk about the tornado, the EF-0. So go ahead, Rodney.
Well, thank you, Joe. Just a brief recap of the event. There was a stored boundary that provided a focus for just repeated rounds of showers and thunderstorms, and it kind of focused along kind of an axis from northern Connecticut into central Massachusetts, and that event actually led to widespread flash flooding across northern Connecticut and central Massachusetts on Saturday, July 17. And, unsurprisingly, a lot of the river levels were running pretty high, and the grounds were saturated from it's been a wet month overall. All our climate sites have already recorded the top 5 wettest July. A lot of places don't need more rain, but that's unfortunately what they received. And looking at the atmospheric setup, there was enough instability and shear, and shear is a change in wind direction and speed with height. So if the wind changes direction or speed with height, then you could get a more conducive environment for more severe storms. And the storms produce, locally damaging wind gusts and, quarter to $half size hail. And also, in addition, the following day there was a boundary that provided a source for a brief spin up, and it led to a brief EF-0 tornado in Somers, Connecticut. And that's what Joe will be talking about later on in the presentation. And here's the radar loop of on July 17 afternoon. And what you're seeing here is so you've noticed the flashes, those bright colors, cross signs. Those are lightning flashes detected by satellite. So where you see there's a cluster of flashes that represent somewhat stronger thunderstorms. And here's a loop of the radar estimated rainfall, for July 17 and 18 combined. And you can see somewhat of a bullseye over northern Connecticut, especially northeast Connecticut. And that was where we received considerable flash flooding. And here's a loop of the what we call the MRMS, maximum stream flow. And this is a tool that we, as forecasters, we like to, use this tool to look at potential places or places that potentially could experience flash flooding. And the bright colors that stand out in the image, those are areas that you want to watch closely. And when you start seeing purple and blue pixels, that represents, there's a huge signal. And perhaps the forecaster or the radar operator would issue a flash flood warning for that area. And you can see some of the green polygons; those are flood warnings that we issued. And this is a tool that MRMS actually is an acronym that basically stands for multi-radar, multi-sensor. So not only does it take into account radar estimated rainfall, but it also makes use of the available stream gauges. So it is really a combination of radar technology and the ground observations, which makes it, which is why it's so useful for situational awareness. And here is another depiction of the how severe the flash flooding is. And notice the bottom corner of the image says return period in years. So what it means is that where you see the purple color in Northeast Connecticut, is suggesting that the flash flooding is a kind of like a 1 in 50 to even 100-year event. So again, that really shows how unusual the event is. And here's a 24-hour MRMS radar estimated rainfall. And as I alluded to earlier, MRMS uses both radar and available observations. So it is a pretty skillful tool that we can use, not only for looking at potential places for flash flooding, but also for the post-event review, we can compare the MRMS to ground observations, and that gives us a pretty good idea of what transpired. And you can see not only there was a bullseye over Northeast Connecticut, parts of the east slope of the Berkshires into central Massachusetts also experienced a lot of rainfall, not just for July 17, but both days combined. And here, there's another, the radar estimated rainfall is it's highlighted, shaded in the different colors in the background of the image, and then the numbers that you see overlaid on the map, those are actual observations from people like you who report to us how much rain you received in your backyard. And also we have the automated sensors that our technicians maintain across the region. And here's looking at some model data. This is from the HREF, and basically the HREF is an ensemble of the various high-resolution guidance that is available to us. So, for example, you may have heard of the HER model, which is the high-res rapid refresh model. The NAM model is also part of the ensemble. So we like to look at an ensemble data because it smooths out the noise from the various individual high-res models, and it generally has very good skill in forecasting what could possibly happen. So in this case, you can see that this is the 24-hour QPF or rainfall total, and it does a pretty good job of depicting where the heaviest rainfall could potentially fall, and it shows a bullseye again across the east slopes of the Berkshires into Northeast Connecticut. So that's a very good job of depicting what actually took place. And here is again, it's from the HREF. This is the 24-hour maximum updraft. And what you're seeing here is that this is the probability of seeing updraft speed over 20 meters per second. And that is usually a threshold to identify severe weather potential. So that you can see pretty much the highest probability is towards the southwest of southern New England and into the mid-Atlantic states. So that was where the severe weather potential is higher. And here is a synoptic observation weather map produced by the WPC, by the Prediction Center. And this just goes to show you, you can see the location of the stored frontal boundary, where you see alternating red half circles and blue triangles. That's the stored frontal boundary. And typically when we see this kind of setup, storms like to form along a stored boundary. And they kind of train over the same location, and that is a huge concern for flash flooding, because if you have rain keeps falling over the same area onto saturated grounds, and you have creeks that are already running higher than normal, that's a classic recipe for flash flooding. And wherever it steps up, that would be a huge candidate for flash flood warning. And that was exactly what transpired. Northeast Connecticut was pretty much under the gun for considerable flash flooding. Here's a map showing the mean layer cape or instability axis. And where you see, you can see a bullseye of 1,500 units of MLK, again, over Northeast Connecticut. And the blue shading that you see, that's the ML-SIN. That's basically inhibition. And so areas where you see the red, that is not that's not overlapped with the blue areas. That's an area of great instability without the inhibition, and those are the areas that you could potentially see storms firing up and continuing for an extended period of time. So again, that just lends more evidence to what actually happened in Northeast Connecticut. You have storms firing up, and they were training over the same area because of the stored frontal boundary. And here, what you're seeing is the 0 to 3 kilometer mean layer cape, and a lot of the storms that took place, they were not necessarily those classic supercell, or like those storms that had very high cloud tops. This is an environment for low top storms, and sometimes it is, if you don't see much instability or like surface-based cape, sometimes it's useful to look at the amount of instability within the first 3 kilometers of the atmosphere. And again, this shows you that there's a pretty good low-level instability, pretty much from, Northeast Connecticut westward into the Mid-Atlantic states. So once again, a good environment for low-top storms that produce a lot of rain. And this is taking a look at the 2 to 6 kilometer maximum lapse rate. And typically we want to see lapse rates of about 6 degrees Celsius per kilometer. That's pretty decent. I mean, it's not overly impressive, but it is enough for storms to develop and sustain themselves. And this is something that is a telltale sign of, we have an environment that is very juicy and could produce a lot of rain. If storms could develop, and notice this is the what we call the P-watts and precipitable water. And notice we have P-watt values of around 1.7 inches to 2 inches. And according to climatology, that's actually on the extreme end of what we can expect to receive across southern New England this time of the year. And this is typically the wettest time of the year, but to see such extreme values, it means that, again, if storms can develop, it could produce a lot of rain in a short period of time. And here's a look at the climatology that I talked about earlier. This is taking a look at the sounding climatology for the recently decommissioned upper air site in Chatham, Massachusetts. That upper air site was taken down because of the beach erosion, and that was, but we still have data from the past decades that we can reference. And again, when you have P-watts of 2 inches, that's pretty much at the maximum range of what you can expect according to climatology for our region. And this is the 1-hour flash flood guidance produced by the River Forecast Center that is actually co-located with us in northern Massachusetts. And what you're seeing here is that, notice and focus on southern New England. So you can see those yellow shadings and actually orange shading. That means that, it takes only 1.5 inches of rain, maybe 2 inches in some locations, in an hour to produce, possibly produce flash flooding. So given the saturated grounds, it does not really take much more rain to produce flash flooding. So that's why, much of the region was on guard for potential flash flooding should training storms develop over that region. And here's a look at the west branch of the Westfield River. And you can see that's actually a classic signature of rapid flash flooding. So basically you have those small creeks that, they might be in low flow, but because the basin is so small, and when you have training storms that drop a copious amount of rainfall in a short period of time, it can lead to rapid increase in the creek level. So you can see in this case, it went from low flow to moderate flooding. So in just a matter of a couple of hours. So that's why for communities that live, alongside the small creeks, you want to be, pay close attention if, heavy rainfall is in the forecast and the grounds are saturated, because a small creek could become a raging river in a short amount of time. You want to be make sure that you're prepared. And this is, and I think that was I worked that weekend actually. So this was actually the exclamation mark on a busy weekend for us. So this is the Malhot River Hydrograph in Warrenville, Connecticut. And look at how it went from low flow to major flood stage in a couple of hours. So, and I believe this was the second highest crest for this site on record. So, it's just, then the highest crest was way back in 1938 and at 14.5 feet. So, but, once again, to go from low flow, 3 feet to just shy of 11 feet in a couple of hours, that's, a classic signature of rapid, dangerous flash flooding.
And Rodney, just to put another comment, if you look at those top 4 crests, the first one that date should stand out. It's the hurricane of 38 and 55, another tropical system too. So not bad.
Yeah, thanks, Joe. Yeah, because considering this is not a tropical system. And we received some pretty dramatic footages and images from social media and the fire chief in that area. This was, actually a tributary to the Malhot River. And you can see this tributary actually washed out the road. And it goes to show you how forceful that river became for the road to be washed away. And this is just a close look at the same road that washed away the road. And here's a Google map image of so point A on the map. That's actually where the road was washed away. And again, that's actually the tributary to the Malhot River. And you can see that the label kind of towards the center of the image. Point B, that's actually Route 44 that crosses Malhot River in Warrenville. That's actually close to the stream gauge that I showed you just now. So, yeah, so once again, this is a pretty dramatic event that caused quite a bit of damage in the area. And this was a social media loop of the same part of the road that was washed away. This is again the tributary to the Malhot River. You can see how, a small creek became a raging river and caused so much destruction. And once again, so this one is actually in Belchertown, Massachusetts, and again, a road that is washed away by a creek that became a raging river.
And Rodney, just looking at this image, we can always go back and see, was the water just to here? No, actually, you can see evidence that the water was all the way up over the roadway. So this was completely submerged all the way back past the roadway. It wasn't just limited to this area here that was eroded away. So pretty impressive.
Yeah, thanks, Joe. And that's why always we tell you don't turn around, don't drown. And this was actually an image sent to us by George Weiss, who works at the WPC, and this was actually taken by his relative, I think, in Templeton on Route 202 on Saturday evening. And you can see the road turning into a river. At this point, I will pass it back to Joe, who's going to talk to you about the EF-0 tornado in Connecticut.
Okay, thanks, Rodney. So the other part, the next day, this was July 18th, Sunday, there was a brief EF-0 tornado touchdown in Somers, Connecticut. Winds were estimated at about 80 miles per hour. Path length is just under 2 miles, and the width was about 75 yards. So a small, brief touchdown. Fortunately, no injuries or fatalities, but caused some tree damage around the area. Just going into the forecast from Storm Prediction Center, just a kind of a general thunderstorm outlook. So no severe weather was really expected. The tornado probabilities you can see here on the left was about less than 2%, but there was the one tornado here in northern Connecticut. Typically, the Storm Prediction Center looks at large-scale severe weather, so covering multiple states, not just localized outbreaks like this. So typically we do talk to them, but if the threat isn't large enough over a big enough area, again, usually at least 2 states or 3 states, they won't really, go too high with their categories. That's where our messaging kind of takes over. So in this case, our messaging was more focused on flash flooding. We had all of the flooding the day before that Rodney showed. We were anticipating another total rainfall of 1 to 3 inches. So really not much, we weren't too concerned about the severe threat. It was pretty low. But so the messaging really just kind of focused on the flash flooding. But both environments can also be, favorable. When we have flash floods, it can also be a tornadic environment. So looking at this is 500 millibars, about 18,000 feet. This is kind of where our steering flow is. You can see there's a pretty big trough here over the Great Lakes, the Northeast, and actually a closed low over northern New York. And it's this pattern that, we've done some research that's shown. This is actually the most common setup for a tornado here in southern New England. Not big outbreaks, but you may see 1 or 2 of these. So a majority of our cases feature a closed low somewhere, usually in southern Ontario or up toward Hudson Bay, somewhere in this region here. So that's kind of our first indication going into an event. If we see this, we should be thinking, potential tornado somewhere. The other part is we had pretty strong jet stream aloft, and it's highlighted here in the yellow. It's in excess of 60 knots, so 70 miles per hour roughly. And the wind flow you can see here by the streamlines comes down the Great Lakes, around the Ohio Valley, and up through New York and New England. So this area on the right, which is our entrance region to the jet where you're going into it, is very favorable for large-scale lift and helps enhance thunderstorms. So the combination of the two really helped the thunderstorms to develop that day. So at the surface, the front, the next day, this is at 8 p.m. Sunday, really didn't move very much from what Rodney showed. Still across northern Connecticut, northern Rhode Island, and we had a little weak low here, and that can usually serve to enhance the low-level turning of the wind from the ground up to a few thousand feet. So southerly winds on this side of the front, easterly winds to the north and northerly winds on the backside. So you can see kind of a rotation here. So as this low moves right across, it really enhances that low-level spin. So we have the combination of the spin, the front nearby, and we had a tropical air mass in place. The dew point temperatures were well into the 70s. So, again, subtle factors, not something that's going to stand out as, a big severe weather day like June 1st, 2011 would have. But, we kind of train our staff to at least be aware of these things and have it in the back of your mind that, there's a flash flood threat, but it's also conducive for probably a weak tornado. So we'll look at some of the analysis maps. Again, this is the instability, similar to what Rodney was showing. You can see the best or highest amount is right across Connecticut. Nice little axis there. So we had some instability through the atmosphere. Also, wind shear. This is looking at essentially what's available for the storm, taking into account storm depth, thunderstorm depth. So 25, 35 knots. This is pretty impressive. You don't always have to have the maximum right over the area where it happened. It can be on the gradient. But still, this is pretty good. That combined with the instability is certainly favorable for severe weather. We'll look at the lowest layers again. This is the 0 to 3 kilometers, so I think the lowest roughly 10,000 feet. And what we look for here is that instability, which we have, but also if you look, it's kind of overlaid with these blue contours, and that's kind of a surface spin. So we look for where we have instability and spin at the low levels to be favorable for tornadoes. And this is certainly right over Connecticut, right in the area where the tornado actually formed. So again, this would have been a pretty good predictor. The overall spin or helicity, this is looking up in just the lowest 1 kilometer. Normally we look for values over 100. And you can see in this case they're a little bit off to the east. But the thing to remember is this analysis from a model is kind of a larger scale. So it's smoothing things out. It's not going to get details down to what we call the storm scale. So things on a local scale or storm scale can spin up pretty quickly. And I think it was more reflected in the previous image than so much on here. So not always going to show up on here, so you have to look at a few other fields to kind of see what's going on. And one other thing we look at in a tropical air mass is the condensation level, known as the LCL. And this is in meters, so 500 meters, roughly, about 1,500 feet. We look for lower cloud bases because lower cloud bases helps a tornado reach the ground much easier than if the cloud base was higher, say a few thousand feet off the ground. So again, this whole area very favorable when they're down around 500 meters. So some of the other guidance that we look at, this is more of the automated guidance, but looking off the SPC page, there's a probability of an EF-0 plus a tornado, and you can see this is conditional on having thunderstorms develop. It doesn't mean it's going to happen, but if you have a storm in the area, there's a fairly high probability, 15%, which doesn't seem like a high number, but these are point probabilities, so they pretty much represent anywhere within about a 25-mile radius. So 15% is pretty healthy. So that indication was there as well. Another field is this one here. This is what's called the Energy Helicity Index. So it's combining what we looked at already, instability and that low-level helicity or spin. And it's got a little bit of a weak signal right near the Connecticut-Mass border. It's weak, but it's there. So sometimes, even if it's not a very strong signal, we still keep it in the back of our mind that, it's not a zero. There's something there. And for storm type, we don't always have the classic supercell. In this case, it was kind of more of a low-topped supercell, but this is more for the, when we talk supercells, what we mean are the June 1st days, the really big severe weather days. This was kind of a weaker environment, but this is favorable too. Highlights, various parameters that are favorable for tornadoes that aren't associated with kind of the classic supercell. So going back, this is what Rodney showed as well for the previous case. Looking at the max updraft helicity, it's kind of a good estimate for where the severe weather is favored. And again, all signs pointing to kind of western Massachusetts, northern Connecticut. Doesn't mean everywhere here is going to have it, and this could be off by a little bit, but it just means somewhere in this region, you really have to keep your eye out for potentials for severe weather, whether it be wind damage or a tornado. Now, we're just looking at a quick snapshot from one of the models. This is the high-resolution rapid refresh. It runs every hour. It actually had the right idea, this cluster of storms lifting north. But this was valid at 7 o'clock. It was about 1 to 2 hours too slow, but overall, that's a pretty good forecast. It's a 23-hour forecast. So this had the right storm mode, and it pretty much had the right location too. So not bad for the HER. So when we start to dive into some of the details, we look at these forecast soundings, and if you've been with us, you're familiar with these. So this is near Bradley, so it's in northern Connecticut. We're looking at going up in the atmosphere. So temperature is the red curve, dew point is the green. Where they're close together, it's very moist, and where they're farther apart, it's a drier layer. And then we can also look at the wind profile. So we have southeast winds at the surface, and gradually they veer to the southwest aloft. So that's favorable. You have a lot of low-level turning. Look at our LCL, that's pretty low. That's below one, again, for about 500 meters. And we have instability here. That's the difference between the red and the blue curve. So we've got all this instability that's available. Pretty much have all the ingredients there. And what the sounding program does is it compares it to past soundings for severe weather to see if there's any, it's kind of almost like artificial intelligence in a way. And you can see potential hazard type, it's kind of keying on a weak tornado. And the line here represents the kind of the energy and the helicity or the spin combined together. You can see, it's right in the median here for an EF-0, a little bit below for an EF-1, but, even a very low risk of an EF-2. So certainly this, should get our attention, seeing this kind of sounding with this kind of comparison in there. So what did the observed sounding look like? This was in the morning from Upton on Long Island, and pretty much tells the same story. It was a pretty good model forecast, even though this is down on Long Island and we were looking at northern Connecticut. Kind of the same environment. You've got the low LCL, you've got plenty of moisture, you've got the instability, and you do have the low-level turning. The winds here were a little bit more out of the south and then southwest, so not quite as much, but still kind of the same profile. And looking at the comparison again, it's keying in on an EF-0 and perhaps even an EF-1, barely scraping EF-2. So this was really, telling us good potential for a very weak, short-lived tornado, which is exactly what happened. So good model forecast. Now let's take a look at some of the radar data. This first one is a loop of the reflectivity. So this is just the storm, the cluster of storms moving north. You can see this starts at about just before 6 p.m., lifting north through Somers, and at the time we had a statement out talking about heavy rain and I think some gusty winds, but not much more than that. Really, you don't see very much that would say this is, cluing you in for a tornado. You could argue maybe, a little bit there of a curl and a appendage, but not much is really showing up. And the thing to keep in mind is from the Taunton radar, this is about 7,000 miles up. So you're not looking at the lowest levels of the storm. We're not sampling it very well. Now, if we go on to look at the storm relative motion, so what this does is it looks at the wind in the storm and subtracts out the storm motion, so you can see the relative motion going on, or rotation. And you definitely see a weak couplet there, especially as it moves through Somers and on north and it weakens. You can kind of see a little bit there, and here it comes, right up in here. The green against the red. Again, not very strong, but there's a reason for that. The radar is off to the east. This storm is moving perpendicular to the beam, so we know from Doppler shift kind of theory that velocities tend to go to zero when you're perpendicular to the beam. You won't sample anything at all. So we are seeing some rotation, but we're definitely way undersampling in here. And in fact, I think the rotational velocity was about 20 knots, when in reality, you could double it. It was probably about 40 knots, which would have been a clear indication there was a tornado present. So that's one of the artifacts of radar. It's not true of just the Doppler radar, but pretty much any radar system that uses the Doppler shift, you're not going to get good velocity data when you're perpendicular to the beam. So we'll just go through a couple of the scans to zoom up. This is at 6:11 p.m. about a minute before, it was after the scan. So this is 6:10. So a minute later, the tornado is going to touch down. You can see it's got a couplet. It's not overly strong. It's not overly tight, but a lot of times with our tornadoes, this is all we're going to see. And this is, again, up at about 7,000 feet. So you're sampling probably above the strongest velocity couplet. I'm sure it was much stronger below this elevation. This is a point where it's on the ground at 6:13 p.m. You can see a little bit more brightness in the color, but again, we're undersampling. It's perpendicular to the beam, so we're not getting good velocity signature here. And tornado's still on the ground, much better here, but it's not tight. Normally I'd want to see this a little tighter, but again, being aloft and not getting good sampling, that's going to degrade a lot of this data. and finally lifted about 2 minutes prior to this image. Still a circulation, but at that point it's kind of dissipating as it heads toward the Massachusetts border. So if you've been with us before and seen our tornado talk, you know we use this kind of detection scale. We use this in real time. It's based on research that we did a few years ago, looking at the environment, looking at radar signatures, and it helps us decide what kind of warning we should issue. It's a guide, but in this particular case, as I mentioned, our rotational velocity, so the couplet, was at 20 knots, which gives us 2 points. We had normalized rotation was up around here. I didn't highlight it, but it was about 0.5, so that's another point. We're up to 3. And then out of the environment, this is our low-level spin. We didn't meet that. Our precipitable water was greater than 2 inches. We did meet that, so we add another point. We're up to 4. The condensation level was not greater than 1,000 meters, and this wasn't a classic supercell structure. So our total points were 4, which would have told us our tornado is unlikely, and we would issue a severe thunderstorm warning, if that, with no tornado tag. Now, as I mentioned, in reality, this was probably 30 to 40 knots. So if we're conservative and say we had a 30-knot couplet, we would have had 6, 7, and 8, which would have said tornado possible, or maybe borderline for the red at 10. At the very least, I would have thought we would have a severe thunderstorm warning with a tornado possible tag. So typically, even if we don't see a strong circulation, if we see something like that and we know the environment's favorable, we'll issue the severe thunderstorm warning with the tornado possible tag. But again, likely underestimating greatly due to the moving perpendicular to the beam and the lowest scan being about 7,000 feet above ground level. So something else, here's another aspect of MRMS, which is really nice. Again, multi-radar, multi-sensor, so we're looking at more than one radar. Low-level rotation tracks, it kind of tracks the couplets seen on all the radars. And you can see there was a little weak couplet that went through Somers. And this is not just taking the Taunton radar, it's taking the Upton, New York radar, which probably had a better sampling of velocity, although it was higher up as well, and the Albany radar too. So it definitely showed some indication of a weak rotation track through the area. Under normal circumstances, like the Cape Cod tornadoes, you'd see a little bit more in the way of reds here, but I think given the radar sampling issue, that's all you were going to see. So we'll finish up here just a couple of videos from social media. These are actually from the tornado itself, and this is from Brittany at 6:21 p.m. You can see actually the funnel there on the left. You can see debris swirling throughout the area, so that was definitely can help us confirm the presence of a tornado. It might be a little grainy, but you can definitely see it there. And here's a better shot from Stephanie, again, sent to us on Facebook. And there's the actual funnel. Not too wide, pretty small, pretty shallow. Again, we're probably sampling somewhere up here, so we're not getting the true rotation. But definitely, you can see there was, it reached down to the ground, so that classifies it as a tornado. And just some pictures afterwards sent to us. This was on Facebook as well. Some of the tree damage, you can see some down pine trees snapped. Nothing really uprooted. So that's why, as part of the damage survey, we concluded the winds were closer to 80 miles per hour in this case. So really just damage to trees. I don't believe there was any damage to residences or in this case. So just to summarize both, we had widespread flash flooding in northern Connecticut and western and central Massachusetts on Saturday. It was the weak surface low and the stalled front that helped us with a little surface spin up, as we call it, and a level shear, leading to a brief EF-0 tornado in Somers on Sunday. And again, the main takeaways that I kind of highlighted to our staff is that the radar velocity data was degraded. The storm was perpendicular to the beam. It's being sampled up pretty high. So as warning forecasters, we need to always remember to take that into account. Remain cognizant of the near storm environment. Remember, we showed that the situation was pretty favorable for a short-lived tornado, pretty classic here for southern New England. So the most appropriate course of action, I probably would have had a severe thunderstorm warning with a tornado possible tag. That's typically how we cover these brief EF-0 tornadoes, as opposed to an all-out tornado warning, which we tend to reserve for the EF-1 and greater. But occasionally, if we see a good signal, we will issue it for those as well. So, and I think the most important thing is the high-res models did a really good job highlighting both flash flood and the tornadic threat over that weekend. So it was a model success story, which was better than last Wednesday, Rodney. So with that, we're going to go and answer some questions, and then I'll hand it over back to Rodney, who will go ahead and give us a weather briefing. So let's see. So we have, this is, okay, question from Landon. How is NROT calculated? So NROT, normalized rotation. So basically what it's doing is looking at the rotation couplet all the way up from the lowest scan to the highest scan that it detects it. And it kind of normalizes it to the depth of the storm. So then we can look at it and use it kind of as a guide. We don't use it as a warning threshold necessarily, but just a kind of a confidence builder. Higher NROT means you have more rotation through the depth of the storm, and the more likely you're going to have a tornado. So that's something that's calculated. Looks like Joe had an earlier comment on the Trenton tornado that injuries reported in the Trenton area. So, oh boy, I hope that's not the case. From Sebastian, radar confirmed tornadoes are rare. Yep, it's hard. Sometimes it's also hard to pick it out. When I showed you the couplet, it's easy when I'm sitting here at home. But when I'm on the hot seat on the radar, you're looking at a lot of data. You've got reports coming in, so it's not always easy to detect. That's why we have a few people on the radar there. Let's see. So from Ethan, I have a question. Mentioned research that was done on tornado potential with the closed low over southern Canada. Is there a layman's description for why that is more conducive for tornadoes, just having an open trough? Sure. So Ethan, when you have a closed low, you're introducing a couple of things. First of all, usually more in the way of tropical moisture, because you're definitely getting that southerly flow up the coast when you have a closed low. So you're getting that kind of moisture coming up from the tropics. So remember, we're going to have that really tropical juicy air in, and also you're introducing more shear, more directional shear. So if you can get the winds at the low levels to go to south or southeast, as opposed to the southwest, you'll get more shear. So when you go aloft with those closed lows, the winds are out of the southwest. So it helps to bring in the moisture and the wind shear, if that kind of makes sense for you. So from Ronald, factors we mentioned for this outbreak are similar. Are there similar factors in place for tonight's event? I'll let Rodney take that one, because Rodney, you've been working on the forecast the past few days. Are we in a similar environment, or is it a little bit different tonight?
Well, thank you, Joe. I would say that there are similarities. For tonight's event, I mean, if anything, tonight's event, the signal is a little bit stronger, especially towards the south coast. Part of the forecast complication is that for tonight's event, there's been uncertainty with how far north the tornadic threat would go, and a lot of it hinges on actually what transpired in the Midwest. There was actually what we call an MCV, that the mesoscale complex system. So basically, it's a line of thunderstorms that produce damaging straight line winds that blasted through Wisconsin and then parts of the Midwest, and then a part of it, right now it's unfortunately causing damage in New Jersey and potentially New York State later on. So in a nutshell, I would say that the environment is actually, I think, a little bit more favorable than the July 18 isolated tornado, and that event actually, that was the only spin up across the whole of southern New England that day, and there was no lightning involved. I wouldn't be surprised to, that we actually have like maybe a few strong thunderstorms tonight. And I will be working radar tonight with Hayden, so we'll be sure to keep you guys safe and informed.
All right, thanks, Rodney. So let's see, as I'm moving on here, just trying to see if I can find more questions. I know we had a few comments on what's going on in Trenton. From Ethan, do we ever make assumptions that there could be a tornado based on a situation where the radar is undersampling of how it works? So the situation kind of with the Somers tornado, if that storm is perpendicular, we're sampling some winds, and we're sampling above, would there be a tornado? Yeah, that's what I was kind of talking about, Ethan. So in other words, when we're looking at radar data, if we know the radar in Taunton isn't sampling it very well, we can kind of mentally say, you know what, I'm seeing a 20 knot couplet there, which isn't, typically that's not too bad, but boy, I'm at 90 degrees, so I know that's got to be a lot stronger. And just knowing that, yes, you would increase the velocity would have to be higher, your coupler would have to be stronger. And you're sampling high. So sometimes surrounding radars can help, but in that portion of Connecticut, it can be kind of tricky because we don't have a lot to look at there. But yeah, that's absolutely correct. Based on who's working, their experience, but certainly knowing it's undersampling, you have to make that correction yourself mentally and know, okay, I've got this couplet, but it's most likely stronger, and I probably need to get a warning out. So I hope that makes sense. From Sebastian, am I correct in thinking that the Somers storm did not likely meet the standard severe criteria? Would it be appropriate to issue a severe warning just for the Torah possibility tag? Yes. So in a lower confidence situation like that, you can still have wind damage. A lot of times what will happen if it's a marginal storm that maybe it doesn't produce the tornado, you can still get a small microburst as the storm collapses. So in some cases, you can have an EF-0 tornado and wind damage from the same thing as the storm kind of collapses and the outflow takes over. So yeah, typically we would do that. You would have some sort of wind damage. And a lot of times in a very weak EF-0, it's hard to tell the difference between the damage. So it's tough for us to go out afterwards and determine if there's a tornado or not. So good question. But yeah, from that standpoint, we typically would see both. Let's see. Oh, John's got a comment. Jonathan's got a comment for you, Rodney. Snow by Anthony Wood, a great summertime fix for snow worshipers. There you go. Thanks, Jonathan. I knew Rodney would like that. Let's see. And Sebastian makes a good comment. These types of cells also difficult to warn because of how quickly they spin up and back down. Exactly. So one of the other things I didn't mention in the presentation was the radar was in what we call the VCP 212, which is severe weather mode. And that gives you a scan every 5 minutes with a lower level scan, if it's in the sales mode. Now, in this case, the radar wasn't put in sales mode because they weren't anticipating in severe weather. So we only had about scans every 3 to 4 minutes when if really it was put into sales, we could have had them every minute, which would have, I think, been a lot more useful too. So I also brought that back to the staff. Remember, even if we're in flash flood situations, put it into the sales 3, it's called, so we get scans every minute and we can get better data faster and really see things changing if they are. Anne Marie, that's right. She had an email conversation with me after the tornado. She drove through the remnants of it. I think it was on the Mass Pike, Anne Marie. So yeah, luckily it had weakened by then. So I think that's what we have for now. What I'm going to do, let's go ahead and